Okay, let's try and solve problem number 2 in the Maple test. So implement the secant method on page 95, so we can go there and look up the pseudocode and try and sketch that out in Maple code. And we should use our implementation to find the root of this funny looking function, and we should find the root that is closest to 0, so that's probably x closest to 0. We should use x0 and x1 as input values for the secant method, and we should find the root within a tolerance of 10 to minus 10 and use 20 degrees of precision. And let's see, for each iteration, print f values and iterate values with 20 decimals. That suggests we should know something about printf. And then there's a hint: try to plot the function an interval minus 10 to 10 to have an idea how it works. Beneficial to use symbolic language. Okay, so maybe we should start out with the hint first. So first of all, restart stuff, and then let's do symbolic. So we will make an expression for the function we have. So it's the exponential of x minus sinus of x. Probably gonna need this later on as a function input for the secant method, so we can just do that immediately. So that's, let's see, sweep unapply of f expression, and the symbol name is x, like this. And if we want to plot our symbolic expression, we're going to call plot. Going to use the expression, going to tell the range we're going to plot, and it was from minus 10 to 10. It's like this. Whoops, that's wrong. I have to do it like that. Let's see what happens. Okay, we get the expression, we get the function, and we get a nice plot, and we can see we have multiple roots. So it's probably the root closest to 0 is somewhere here. So I guess it makes sense to use these input values for the secant method. Okay, so let's try and write the secant method. So let's give it a name, mySecant equal to procedure. Probably gonna need a lot of parameters, but we can just sketch out the raw stuff first, like this. So let's see, we need some input. We need 2 consecutive iterates. We need the function we're gonna solve the root for. We need epsilon tolerance, and let's just give it some default values. We're going to use keyword parameters for this, and another tolerance. Also going to use a keyword parameter for that, some default value. And as usual, it's a good idea to have a maximum iteration count. That doesn't hurt. Okay, so we need a while loop somewhere, and I guess we need an iteration counter, like this. And let me see, we probably also need to declare an iteration counter somewhere. And we probably need to increment this iteration counter correspondingly, like that. And then it might make sense to have some local variables we can use for updating the 2 past iterates. So we're just going to initialize these to the current input values. Also gonna evaluate the function values. Like so. And let's call that f1 and f0. Then I will probably need to compute a new f value, some new guess, I would imagine. Okay, then let's see the basic idea. We need to come up with a new guess for new iterator. Probably also need something to store that in. Could be something like this, for instance. A C, set 2, probably from set 1 minus, and then we need the secant formula here. That's pretty much a write-off from the equations in the book. Bit mindless. We need the function value and the new iterate. And then we should print out something. And we should print out the iteration counter, function value, the iterate value. And we need to print those. Let's see, its iteration is an integer, something like this. And the function value should be something like this. And let's see, it's a float, and we needed, let's see, was 20 decimals. So that's like this, I think. And the same for the root. There you go. That should be about it. And let's see, what more do we need? Might be a good idea also to have a print statement. If we run out of iterations, that would be down here. Let's say not enough iterations, like this. And I guess if we get to this point, we should just give up with whatever best root we have so far. So that would probably be set 2. Let's see, we need some stopping test here. So if the, let's see, absolute value of if of set 2, that's like this value here. If this is less than the epsilon, or if the spacing between roots gets too small, then we can basically hold, and there's no point in continuing to do the iteration. That would be like this, like that. Then we need to update the iterate. So set 0 would become set 1. Set 1 would become set 2 for the next iterate. Similar for the f values. Like that. Okay, we have most stuff in place. I think there's one thing missing. Oh yeah, so the version in the textbook about the secant method is basically always making sure that values or iterates their flip such that if, again, this is just basically a write-off of what's already sketch and pseudocode in the book. So it's not really big thinking here, it's more like copying. What it will do. So this is a swap of the Z value and a swap of the F value. It's gonna make sure that the F1 is always the biggest value in an absolute sense. Okay, I think this is pretty much the secant method. I think we made an implementation here. Let's see if we made any errors. So far so good. Okay, then we need to call the method, and we need to use as input for x0 the value minus 3.5, minus 2.5, minus 3.5, or minus 2.5 function, and we needed to find this up to 10 to the minus 10. Okay. And for epsilon, there's no specification for that, so we can just plug in some value for that. I don't know what to use, let's just pick something and see how it goes. And first run around is always not a very clever idea to use too many iterations if we have some errors. So let's see what happens. Error minus expected. So we got some, it's this thing here. Let's just rewrite that. Let's see what happens. Okay. There's something wrong. Let's see what is this. What does this say? It's true or false? Okay, so it's the expression coming from this one here. Let's try and debug this a little bit, just to figure out what goes on here. Let's just crank this down. Okay. So it seems it's not really evaluating the if function here. So what are we passing in? Oh, this is the error. This is a symbol, it's not defined. I need to use this one. Hey, now it looks much better. So let's crank up this one to like 10 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's fine. Let's run it. And let's see. Something else is amiss here. I'm just gonna move this. And then let's have a look. It's probably because I'm only running 3 iterations. And the output looks kind of ugly. So let's make a new line here. New line here. correct that spelling. So still something wrong. Maybe I did not compile the function. We'll try to do it like this. Okay, so still need more iterations. Let's do 10 iterations. And it seems like we're running now, so we can remove this extra output we get out. And there's no need for us to make this output here. So let's see what happens this time. And we can see we are getting out, we iterate here, minus 3.1830, blah, 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 blah. Let's just look at the plot. Minus 3. That looks just about right. So that makes sense. And we can see the function value is very close to 0, too. That's problem number 2 done. Let's just check. Yeah, everything done here. No worries. We can go on